exactly. If x1 is 1, x2 is 1. If x1 is minus 1, x2 is minus 1. So x2 is literally just a copy of x1. Okay. Yeah.
Oh, okay. So they're always the same value.
They're always the same value.
Okay.
Yeah. Yes?
So we fill in the distribution table as though they were just independent variables with similar distribution.
You don't know anything about the distribution. You don't know upfront anything about the distribution, right? So, I mean, as when you're filling up the table, you just assume that there are two different variables and you're getting data from naive base.
But
I mean,
I would never get an example of -1, 1.
You would never get an example of -1, 1, but you will still get a probability for that, a non-zero probability for that.
Are we doing smoothing?
No, even without moving. Because you never look at the pair -1, 1. You look at -1 and the lid. 1 and the lid. Right? So you look at the feature x1 equals -1 with the probability of x1 equals -1 given some label. The probability of x2 equals 1 given some label. Which means if you multiply.
Okay, so that's the same as just looking at them as though their distributions were identical.
Oh yeah. That's
Okay.
right. That's right. Yes.
That can never. You wouldn't have a just probability that can never happen
You
by the definition of the problem.
you will not have a probability what?
That one would be different from the other.
You will not have, see, that's the thing, that's the part that I'm asking you to confront in this whole question. So, if you have x1, x2, and y, yeah, sure, you'll never see an example that looks like anything of this kind. That looks like this kind, anything of this kind, right? But, when you do your counts, what is the probability of this particular example according to the naive Bayes model? The naive Bayes model says probability of this is probability of y equals whatever that was times probability of x1 equals plus given y times probability of x2 equals minus given y. Sure, in reality this should have a zero probability.
Okay.
But in practice, this product is not going to give you a zero probability. And this is where naive Bayes disagrees with the real world.
Okay.
Naive Bayes is just a model of the real world. Like everything else. Everything that we are doing is just a model of something that exists. Other questions? So this question that you guys are asking about can be either the easiest question that you've ever seen so far in the class or the most confusing one. If you're just mechanically going to not think about it and just apply whatever you saw about naive Bayes, it's extremely easy. But once you start thinking about what it means, it seems so weird. And a lot of people are happy are finding it difficult, which is good, which means that you're actually thinking about it. Any other questions? Yes?
The stochastic gradient descent, do we just one example during one epoch?
No. Each epoch, you shuffle the data and then you iterate over the entire training set. And after the end of the epoch, you calculate the objective, the negative log likelihood, on the entire data set.
But we need to change weights based on one example, right?
Yes. That's right. Just like with SVM.
Just with SVM we had on slides, you only had chose one example, then change weights, and then repeat for each epoch.
Yeah, but that example still had a subscript I, which implied that we were choosing all of them in that epoch.
So, I don't know if you answered the question, I'm not sure what. So let me just quickly write down what stochastic gradient descent might look like. So, you initialize your weight, let's say 0, you have to think about that stuff, and then for each epoch, shuffle the data, and then for xy in the data, w is w minus the gradient of the loss. And then, so this is step 1, step 2, and then here compute negative log likelihood for your plot.
So we calculate gradient for each example?
Yes. Yes, that's right. You this gradient here, you pretend that your data set is that one example and you calculate the gradient. And that's your estimate of the gradient of the full data.
Aren't we taking for each example belonging to the data? So how is it only one example?
Well, this is with respect to one example. So here, this is of W, X, Y. So this part here is for the example XY. So the loss is computed with respect to, the gradient is computed with respect to that one example.
Okay, so each example will go one by one.
Yes.
And then, okay.
Right. Other questions? Yeah.
So the negative log likelihood is just the log part of the objective?
Yep.
Why do we want to look at?
Oh, it's not just the log part of the objective, it's log of it's the full objective. The negative log likelihood is actually the entire objective. If you think about how we derived the negative log, the logistic regression, we are maximum, oh, that's right.
It's the math.
Oh, you're right, actually, yeah. I just realized that I shouldn't have said negative log likelihood, I should just say plot the objective. If you have not yet done this, plot just the objective, right? If it's the, okay, let me just write this down. That's a good point, and in fact, so you have, the objective is half W transpose W plus, is it half? This is sigma squared. Yeah, 1 over sigma squared. Plus sum over your entire data set log 1 plus e power minus pi. Right? I want you to plot this. I want you to plot this at the end of the epoch. You're right, the negative log likelihood by definition is just this part alone without the regularizer.
Yeah.
And that might be the reason, Max, why you saw some weirdness when you were plotting stuff. Yeah.
So while doing training, we choose the best accuracy, and for that we do the plot.
No. So when you're doing the training, you make one entire pass through the data.
So we're doing cross-validation.
Oh, you don't plot during cross-validation. You just get a bunch of jumble. So you do cross-validation, get a good enough sigma, and then plot only on the training run. So you have the best sigma, or whatever the parameters that you have.
Choose the best one.
Choose the best hyperparameters, and then train on the entire data set and give me a plot. And just to reconfirm this, and probably Max, you should post an announcement. I don't want you to plot the negative log likelihood, I want you to plot the entire objective at the end of each epoch. Yes.
So I noticed that when you include shuffling, so without shuffling, the plot of this is nice and smooth. When you start shuffling, it goes crazy. Why is...
So shuffling is important. Without shuffling, the stochastic gradient descent need not converge. So it might be why, and usually the what do you call it, the objective for stochastic gradient descent, when you plot it, not just for this, for any sort of objective, when you trace the objective for stochastic gradient descent, it will be wobbly, but the size of the wobbles will decrease as the training goes along, partly because your learning rate is getting smaller and smaller. Which means that as you go along, eventually, if you plot it long enough, the learning rate effectively is insignificant. So it does not change, should not change the objective too much. But the objective will wobble. But there's only one wrong answer to this, which is you're minimizing the function and your objective is going up. Does that make sense? If your objective goes up, that's a good way of knowing that something funny is happening. Other questions? That's a good point. Just to remind you, plot not the negative log likelihood, but the entire objective. at the end of each epoch. The reminders, there's a project report that's due on the 15th. I changed it last week. And those of you who are doing the competitive project, I changed the deadline for the Kaggle thing submission also to the 15th. And I think, as I just was talking about this, there's a restriction of 3 submissions per day. So if you haven't made any submissions, or if you feel like plan ahead. There's a restriction of 3 submissions that you can make per day. Any algorithm that we see in class, I expect you to implement it. I know there are actually industrial strength implementations of all these algorithms out there in public, in the tools, and you can use them after the semester is over or for your own entertainment. But for your projects and your homeworks, just a reminder, if we see an algorithm that we have gone through in the class, I expect you to be able to implement it. And in your report, you should tell me about how you implemented your algorithm. Spend a little bit of space in your project report describing the design choices. For example, did you use for your perceptron or SVM or whatever, do you represent your weight vector as arrays? Do you use something like CUDA? Do you, for example, use hash maps for your weight vectors or anything like that? Yes?
So just to be clear, what you just said was that if we're using the algorithm we see in class, we should describe it fully.
No, you should also describe the implementation details.
Okay.
There's a difference between just the algorithm and the choices that you make when you implement it.
Okay, you're not saying that we should implement every algorithm we've seen in class?
No.
Okay.
We should be able to, but and in some sense you have already probably done most of the algorithms you've seen in class for your homeworks. For your projects, I want you to use what you implement.
Okay.
There are, with respect to the competitive project, I see that the best performance now has hit 90% on the Kaggle competition, and feel free to share tips and tricks with each other. It's called a competition, but it's really a group learning exercise. So there's no reason to not share something cool that you found about the data. Yes?
Does that mean an F1 score of like 0.9 or?
An F1 of 0.9.
Okay.
Yeah. And of course, since we are measuring F1, you should be doing cross-validation on F1, not accuracy. And finally, there's an exam in the class on the 14th. It's at 8 a.m. Please show up on time. I certainly will. And it's a closed book exam that will cover everything that we did not cover in the midterm. So everything from learning theory. Yes?
Are we allowed to bring notes?
No.
What, is this Thursday? Are we going to have a review session? Or?
This Thursday, we're not going to have a review session. Instead, I'm going to talk about the practical aspects of applying machine learning.
Okay.
Most likely what I will do is I'll convert my next office hours on Tuesday to an open discussion sort of session.
Okay.
So that's not today, but the next office hours.
Okay.
Yes, will there be some kind of review sheet or?
I'll make a review sheet and post it on campus. And the review sheet is actually very easy to make. I just take the titles of all the slides. So, some people really like it, some people hate it, but sure. And to be honest, just very frankly, I think the exam's important to give you grades and stuff, but I'm more concerned about what you learn in the class. Which is why I don't want to, I'm not particularly keen about reviews and stuff. I say that the exam will only cover things from learning theory and stuff, but it does not mean that you should forget everything that you knew about linear classifiers, or that you should forget everything that you knew about decision trees. Alright, so let's...
One more question.
Okay.
I guess the better question would be will there be any hints as to what proofs we should study more than others?
All of them. All of them.
Great.
Each one of them is important and beautiful.
Yes.
And they're really like the fundamental. There are only few fundamental ideas that are that underlie all the proofs. Rather than studying the proofs, I want you to understand why the proof works. That's easier said than done.
On the midterm, there was a proof that kicked everybody's butt, so. it's just one.
Which was actually a minor variation of perceptron. But anyway. Alright, so let's talk about, let's go back to where we were. I want to wind up this lecture on neural networks that we had in the last lecture. So we looked at the backpropagation algorithm. In fact, I did not write it down as an algorithm. Instead, I actually stepped through the process of backpropagation. And backpropagation is this computational trick for computing gradients. So I give you a loss function and ask you what is the gradient of that loss function with respect to the parameters for a particular example. And backpropagation is a way of automatically computing gradients. What underlies backpropagation are two fundamental ideas. The first one is that you can, the chain rule. The first idea is the chain rule, which you are very familiar with. It's if you have any function f, and this is a function of another function g of x, then the partial derivative of f with respect to x is the partial derivative of f with respect to g, and the derivative of g with respect to x. And backpropagation requires you to apply the chain rule again and again till you get down to something, to the variable that you care about. The second thing, the second idea that drives backpropagation is that if you write derivatives this way, some of these partial derivatives you will see are things that you've already computed for something else, for another variable. And you apply the greatest trick in computer science, which is don't do the work unless you have to. You've already done one partial derivative, so you just cache it. So you memorize partial derivatives. And in fact, you don't even have to memorize it. You just, if you go down the neural network from top to bottom, you'll just keep track of all the computation that you've done so far, and that's it. In fact, you do have to cache it. So it gives you the gradient, and remember that backpropagation is just a way of calculating gradients. Once you get the gradient, you need to do something with it. And we know what to do with gradients. We can apply it in stochastic gradient descent. So stochastic gradient descent is a generic learning algorithm. What we have done is we've taken the problem of inventing learning algorithms and reduced it into this question of writing down objectives. And there is a whole library of objectives for you to choose from. You can choose the log laws like logistic regression. You can choose the hinge laws like SVM and so on. And you can play with regularizers. You can add a regularizer. You can choose not to. You can add a different kind of regularizer. So you have this plug and play sort of an infrastructure for writing down objectives. Once you write down an objective, how do you optimize given a data set? You use stochastic gradient descent. The only difficult part of stochastic gradient descent is computing the gradient. And so far in the class, we've been, for all the simple classifiers like SVM and stuff, I've been deriving the gradient manually. For logistic regression, you are deriving the gradient manually. Backpropagation is just a way of taking this idea of deriving gradients and making that also a computational process. So backpropagation is a generic method for computing gradients. So what this means is we now have reduced the problem of inventing learning algorithms into the problem of writing down objectives. Because once you have an objective, you use stochastic gradient descent, you use backpropagation, you have a learning algorithm. Backpropagation itself is recursive. You go from top to the bottom of the neural network. And the nice thing is most modern neural network libraries like TensorFlow have industrial strength implementations of backpropagation. This algorithm is a bit of a pain to get right correctly because it requires a lot of bookkeeping, and these people do it for us. And one could argue that if all the stuff that you hear in the news about neural networks is possible because we have this generic way of inventing, exploring hypothesis spaces. Remember, every neural network defines a hypothesis space and using its architecture. So by changing the network architecture, you are effectively changing the hypothesis space, which means now you have to, if backpropagation did not exist, you'd have to rederive everything from scratch, and that's a painful process. Because we can do this automatically, we can, we've seen this explosion of exploration of network architectures, and you get these crazy networks that are 150 layers deep and have interesting connectivity patterns and stuff like that. And the reason this works is because we don't have to keep deriving the gradients. So just to put everything in context again, we have a neural network, I'm calling it NN. A neural network is just a function that takes an input, it's parameterized by some weights, and just to keep the convention going, I'm calling them W. And it produces a label. For that label, we can now write down a loss function called L. And our goal is to minimize the total loss over the entire data set with respect to the weights. Perhaps there's a regularizer, I chose not to write it because I don't have space. And SGD works exactly the way it works all the time. You initialize the parameters and you run the algorithm for multiple epochs. You shuffle the training set and you pick an example. This is exactly what we were talking about earlier. And you pretend that this example is your entire training set, and you compute the gradient of the loss function using backpropagation, and you make an update. And SGD had all these nice guarantees when we were doing SVMs and logistic regression, because the objective, that is this function here, the one on top, was convex. With a neural network, we no longer have a convex function, almost always. But you have a function, you have a gradient, you can go down the gradient, you will get to a better place, then that's what happens. We don't have guarantees of optimality anymore. The second thing is with respect to the learning rate, and the usual kind of tweaks with respect to learning rate are possible. You've seen one or two of these, and there's a whole cottage industry of picking the learning rate in just the right way. And then there are other variants of this gradient descent idea that are quite popular. If you read literature or if you read any tutorials on this stuff, you'll see words like adagrad, dropout, momentum, and such things. These are all sort of tweaks on this basic template. And I'm not going to cover all of these because we don't have time, and it's like an entire semester's worth of class to cover all the tricks and tips with neural networks. But hopefully I've given you enough of skeleton for you to pick it up. Any questions about this? Yes?
So, like for SVMs, if the stochastic gradient descent doesn't work, you know what to look for. The objective
Debugging neural network optimization is much more complicated.
How do you do it?
How do you do it?
Do you just get it right, or?
No, you don't just get it right. Nobody just gets it right. There are multiple ways of debugging. One of them is the following. Even though the objective is not going to get to a global minimum, typically it decreases. So if you don't, I'll get to that in a minute. I'll get to the practical aspects actually right now. So there are many practical concerns with using neural networks. This is, I don't know if I mentioned this in class, this is one of those areas of machine learning where empirical science has gone faster than theory. So if you guys, any of you are interested in doing any theory of machine learning, and you want a particularly challenging problem that will keep you busy for 5 or 6 years, think about the theory of any theoretical questions with neural networks, because most of them are unresolved. I'm going to only talk about 3 of them. One of them is addressing concerns with stochastic gradient descent, and then I'll talk about how to deal with overfitting and how to find out what's the height and the width of the network. So there are no guarantees with stochastic gradient descent. The function may oscillate, it may get to a local minimum, and the thing that we should keep in mind is, in practice, when we train neural networks, we usually train them on massive data sets. Typically neural networks, the bigger the really large neural networks that you hear about in the news are trained on really huge data sets. And sometimes you require like several thousand epochs. You may require many hours of CPU or GPU time. In fact, NVIDIA has now invested heavily in creating customized hardware for deep neural networks. I think they just earlier this year they released or they announced a deep learning supercomputer built entirely out of GPUs that you can buy if you have about 150K lying around. But the point is, training is going to be very, very slow. I am aware of cases where it even takes weeks. The one thing you can use is, so first of all, how do you know how do you know when learning stops? How do you know that you should stop after 10 epochs or 10,000 epochs? One way of doing that is to keep a validation set, keep a little piece of the training set that the learning algorithm does not know about, and you evaluate the objective on that. And once you see that the error, or you don't evaluate the objective, you even evaluate the error. And once you see that the error stops decreasing or actually starts going up, you say learning is done. And you use the penultimate parameters for learning. Question?
No, never mind.
Okay. So the other thing that you need to think about is how do you avoid local minima. And this may seem like a weird way of doing this, but this is a non-convex problem, which means your answer depends on the initialization. And what people do is you start with different random initializations, and you run the the gradient descent using all of them, and you pick the one that has the best objective, or you train all of them, you have all the neural networks that are trained, and you create a committee out of them, and things like that. So basically hacks. Does that sort of answer your question? I mean, this is just scratching the surface. There are multiple public papers that are entirely devoted to the practical aspects of training neural networks. Oh, by the way, the webpage for this lecture, I've put up a link to an online book on deep learning. It's probably, to my knowledge, the most exhaustive collection of these kinds of information about neural networks. It's available online, you should check it out. The other question is, how do you prevent overfitting? Remember, a neural network is still a hypothesis space. It's an extremely expressive hypothesis space. It can express any function, which means if you're not particularly careful, your network will overfit. You need to figure out, you need to actively try to not overfit. One way of doing that is to keep a validation set again, and keep track of accuracy after each epoch. And when the performance on the validation set goes down, you return the parameters. You basically remember the parameters after each epoch, and you return the parameters of the best neural networks and you return the best parameters according to error on the validation set after the error starts decreasing. The problem is though, if you start having different validation sets and do cross-validation and all that, you don't do cross-validation. Suppose you don't do cross-validation, you just have this one validation set. You effectively are giving up training data in order to do this kind of hyper-parameter selection. And of course, the one way of doing this, of addressing this is something that you are extremely familiar with, which is cross-validation. You don't do validation, but you have k-fold cross-validation, and you do cross-validation to figure out the number of parameters, the number of layers and the number of epochs and all that, and then you train on the full data. The problem with that is, if one round of training takes a week, k-fold cross-validation, 5-fold cross-validation is going to take 5 weeks. And then you get the hyperparameters. At that point, you train the thing on one. It's not going to take 5 weeks. Actually, it's going to take much, much longer. It's going to take 5 weeks for every hyperparameter choice. Which is why you suddenly start seeing reports of how you take a month, 2 months to train a network, and then you found that, oh, you know what, I had one layer too few. and then you start the whole process again. This is why neural networks are like very heavy on the computational workloads, and that's the reason why you see this new research directions on how do you build customized hardware geared towards neural networks, these kinds of workloads. Similar sort of thing about the number of hidden nodes. If you have very few hidden nodes, then your classifier may not be able to express really complex things. At the very extreme, if you have a two-layer network, something that looks like you have an input layer, these are all neurons, you have a hidden layer, and then you have an output, and this is fully connected, and this goes this way. Let's say the hidden layer has only one neuron. If the hidden layer has only one neuron, you might as well not have the hidden layer. You should convince yourself that it's pointless to have just one neuron in the hidden layer. So too few is a bad idea, because it will underfit. Too many will overfit. So what's the sweet spot? Once again, cross-validations. Now you use cross-validation to figure out the number of hidden units in each layer. So as this is getting clearly repetitive, let me just summarize this general point. There are a ton of hyperparameters that you have to deal with when you're dealing with neural networks. It could be things like number of layers, the number of neurons in each layer, connectivity across layers. You may choose not to have fully connected layers. The loss function, the input features, and it keeps going, and all the other stuff that you had, the trade-off parameter between the regularizer and the loss, and all those things. And picking the right hyperparameter is extremely important to get good performance, and the usual answer in the neural network universe is you get the best hyperparameter by doing massive cross-validation. And that's pretty much all we do all the time. Questions? Alright, so let's just wrap up this section on neural networks. What we saw was, we looked at the definition of a neural network. It's basically multiple layers of neurons, where each layer, you can think of the inner layers as being ways to learn the features or representations of the data to facilitate classification. And this is a highly expressive hypothesis class. And you should think about whether extremely high expressivity is always a good thing. The answer is of course no, because the VC dimension gets very high and you will overfit. We looked at a sort of a big high-level overview of how one might train a neural network, and the underlying difficulty was how do you compute gradients, and the answer to that was the backpropagation algorithm. What we did not see is actually a ton of stuff. This is a very huge area, very fast moving, and there are new algorithms and tweaks and stuff like that keep getting invented every day. Right now, there's a conference going on in Barcelona called Neural Information Processing System. This is the top tier machine learning conference, NIPS. And if you look at the proceedings of NIPS, you'll see that a majority of the publications in NIPS are some new idea about neural networks. My hope is that, of course, it's humanly impossible to cover all of that in a class. My hope is that we have looked at enough of the basics that you can now read some new things on neural networks and pick up on it. One thing that I did not cover, and with some reason, is I did not talk about any specific named neural network. You will see network architecture, and by named I mean there are certain architectures or certain families of architectures that seem to be well suited for certain tasks. You will see, for example, one of them is called a restricted Boltzmann machine, and very closely related to that is an autoencoder, and this is a way of learning a latent representation of the data. A convolutional neural network is a neural network that has some lineage in computer vision, and it's based on, it's a neural network whose architecture was developed was inspired by the mammalian visual cortex. And this is a neural network that has really, that revolutionized computer vision, or at least object detection in computer vision. Before that, people used to have, standard old-fashioned machine learning, things that you guys know and love, methods that you know and love for detecting whether there's a cat in an image or not. In 2000, and they have a competition called ImageNet. ImageNet is this yearly competition where different teams across the world compete for bragging rights about how well they can identify objects in images. Until about 2010 or so, the standard, the best methods were based on what might be called a variant of a support vector machine, a structured support vector machine actually. And 2011 was the first time the convolutional neural network took the top spot, and it was a massive margin between that and the second best. And from 2012 on, every team that competed was using a convolutional neural network for this problem. You see things like recurrent neural networks, which are used to model sequences. You'll see recursive neural networks, which are used to model more compositional objects like language. And you'll see words like long, short-term memories and memory networks, and this keeps going on and on and on. And if you're more interested in this, I recommend that you read the book that I've linked to on the class website. One thing that I have to add is, please don't fall prey to hype. There is a lot of interesting stuff happening in the neural networks world, and there's way more press releases. So don't get your research from New York Times. Get your research from peer-reviewed publications. And in the interest of time, I do want to actually make this point a little more strongly. This was a news article from New York Times, or actually New York Times from 1958, that said a psychologist grows an embryo of a computer designed to learn and grow wiser. By the way, this was the perceptron algorithm. The same thing, the perceptron in New Yorker, I think. The first non-biological object which will achieve an organization of its external environment in a meaningful way. It might be useful to send one to outer space. 1984, computer scientists stymied, again New York Times, this time this is the AI winter. This was the time when they said, this machine, at that time it was not called machine learning, it was called pattern recognition. Pattern recognition is bogus. Computer scientists have failed to master vision. And then suddenly, 2012, deep learning sees progress. The hyperbole is identical. You could have taken these news articles from 1958 and released it in 2012. It would be hard to tell the difference. Same thing again. This is Yann LeCun's. Yann LeCun's one of the pioneers of deep learning. He's the guy who pushed for convolutional neural networks as a way of doing computer vision in 1984 or 86. And I'm going to read this quote out because it's important to keep this in mind. Artificial intelligence died 4 times in the last 5 decades because of hype. People make wild claims and could not deliver, and the ensuing backlash, and then there's the eventual backlash. It has already happened twice with neural networks, once in the late 60s with perceptron, and once in the late 90s, nothing named, but what happened in the 90s was support vector machines basically took the brunt of the hype. So don't let it happen again. Please be aware of the hype. And the fundamental mathematical concepts don't change. So this is just world wisdom. There's no machine learning in this slide. I just want you to keep this in mind. All right. And the reason I put this, I would have actually put this in the last lecture, but I wanted to specifically put this at the end of the neural networks lecture rather than at the end of the semester. So, any questions about neural networks? Not. I'm going to take the time that's left to talk about the absolute last classifier that we're going to see in this semester. And the easiest classifier that we'll ever see in the semester, and also the oldest classifier that was invented, the nearest neighbors classifier. Talk about the k-nearest neighbors classification and about something called Voronoi diagrams, and introduce you to your final machine learning concept, or final sort of a mind-bending concept called the curse of dimensionality. Just out of curiosity, how many people have used k nearest neighbors before? How many people have seen recursive dimensionality before? Okay, not the same set of hands. That's good. So, those of you who've seen k nearest neighbors, please don't answer. The rest of you, let's say I have a bunch of colored circles, and 2 of them or 3 of them don't have any colors. A, B, and C on the slide. These 3. How would you color A, B, and C? What's the color for A? B? Red. And C? Why?
I guess we choose the one nearest neighbor, then that's,
I don't know what a one nearest neighbor is.
neither do I, but I'm just saying.
But yeah, so in some sense it's an intuitive idea. You want to color the point, you look at its neighborhood, and you see what the colors are, and you just give the color of the neighborhood to that point. So, you are all right. This is easier than an exam question. But in some sense, you can think of the points that you already have in the training set. All the colored points are the training points. The points that you have in the training set effectively partitions the entire space of points, the entire instance space, into red and blue points. Right? A point that you've never seen before, something here for example, you know that it's blue because it's in the blue region. The closest points to it are blue, so it must be blue in the absence of any information. So that's it. That's the idea of nearest neighbors classifier. You have points associated with labels. You have XY pair. That's your training set. This is the easiest learning algorithm you can ever think about. The learning algorithm is the following. You read the data and put it in memory. Done. That's it. The learning just involves storing the data in a way that you can easily access. And unless you want to be particularly clever about it. Prediction is the following. When you see a new example, you go over the entire training set, you find the point in the training set that is closest to the test point, and you return the label of that point. So you remember the entire training set. When a new example comes in, you iterate over the entire training set. You find the point that's closest to your test query point. It has a label because it's from the training set. So you return the label of that point, and that's it. Questions about this algorithm? By the way, this is called the one nearest neighbors algorithm. This is the easiest learning algorithm ever. Okay? K nearest neighbors is just a minor extension of this. The training is the same. You just store all the points. At test time, when a new example comes in, you don't find the closest point, you find the K closest points. And that's slightly more tricky, not that much more. You should think about how you will do that. And you have K training points, and you have to construct the label for this new point using the K training points that are closest. If it's classification, how would you do it? Voting. You take the majority label. So you have K points, all of them have some label. You take the most frequent label in that lot. Yes?
So when you find the K nearest points, are they all weighted equally when you're deciding?
Good question. In the vanilla version, yes, but perhaps they need not be. How would you do this for regression? If each training point, if the yi was not a label but actually a number, and your training points all came with a value associated with them, how would you, and you have K of them, how would you make a prediction? Take the average. That seems like the most obvious thing to do, and that's basically it. So, in some sense, I have covered the nearest neighbors algorithm. Right? You should be able to implement this even with what I have just told you. And in fact, okay, there's a question there first and then. Sorry? How do you measure the closest? Good question. In fact, that's the $1 million question when it comes to nearest neighbors. How do you measure the closest? And I'll get to that in a minute. Yes?
Once you know how close they are, couldn't you scale the vote? Couldn't you have the vote decay based on the distance?
You
from the
could.
point?
In fact, that's a variant of this thing.
Okay.
You could weight each of the neighbors by how far it is from the test point, and that influences how much, and that weight is how much the vote that point gets for the label. So nearest neighbors is like the prototypical example of a class of learning algorithms called instance-based learning. And instance-based learning is the following idea. When you want to learn, you store all the learning involves just storing all the training set examples, and prediction is when a new example comes in, you discover somehow similar examples that have in your training set, and you construct a prediction using the similar examples. Some people also call it lazy learning because if you don't have to do any computation upfront. All the computation happens at prediction time. Of course, if you want to be actually efficient about this, you might want to somehow index your data cleverly so that this lookup eventually becomes easy, but if you don't feel like doing that, you don't have to. It will be slow, but yeah, sure. Questions? Yes?
So could you explain a little more about the regression case?
The regression case is the following, okay? Let's just go back to the picture, and instead of blue and red, let's say you have a number associated, okay? Let's go to this picture here, and instead of blue and red, let's say each point has a number associated with it. Let's say this point is half, this point is 1/3, this point is 15, and this is 3. And now for the test point A, let's say I do k nearest neighbors with k equals 3, so 3 nearest neighbors. So this is my test point. The 3 nearest neighbors, let's say, are these 3. At that point, let me make my life a little easier and not make complicated fractions. 2 and 4. I find the nearest neighbors. I found 3 of them. I look up their labels. I get 2, 3, and 4. And the prediction is the average of these three things. So 3. So then I'll predict. The prediction is 2 plus 3 plus 4 divided by 3, which is 3. Okay. So the question that you asked earlier was the important one. How do you know what's a good way of closest? What does closest means? And to get that into place, you need to somehow define the idea of a distance between the points. This is usually a good place to inject any sort of domain knowledge into the system, into this classifier. And the behavior of the nearest neighbor classifier often ends up depending quite heavily on how you define distance. So if you have numeric features, let's say, if you have features that are just numbers, vectors, points in n-dimensional spaces, how do you define distance? What's the different distance between 2 points in the space? You can take the norm, that's called the Euclidean distance, the square root norm. That's just the Euclidean distance, which is you have. And I'm going to work through this slightly in detail just to make the next point. You can have, if you have x1 and x2 as 2 points, you have 2 vectors. Let's say x1, 1, x1, 2, x1d, and x2, 1, x2, 2, x2d. These are 2 points, and the distance is simply defined as you take the difference, so x11 minus x21, difference squared, and or in fact in general you take the squares of all the element-wise differences, add them up, take the square root, and that's the Euclidean distance. You've seen this multiple times, and this must come as no shock to you. Okay? So, any questions while I'm erasing? Too late. But that's not the only way to compute distance. Another way of doing that is something called the Manhattan distance, which is you have 2 vectors. I'm going to write them down here: x11, x12, all the way to x1d, and x21 to x2d. I can take the difference take the absolute value of the differences and add up the absolute values. Basically coordinate-wise absolute values. So if you have 2 points, let's say you have, let's say this is 1, 2, this is 1, and this is 2. Let's say I have 1, 1 and 2, 2. What's the Euclidean distance between those 2 points? What's the Manhattan distance? 2. The Manhattan distance is you move along one coordinate till you match up and then you move along the other one. It's also called the city block distance.
Is it also called taxi cab?
It's also called the taxi cab distance. So it's just another way of computing distances, and who's to say that maybe for your problem, that the one that you care about, it's the Manhattan distance that's going to give you the right answer. Notice that changing the distance measure will change the way in which the neighborhood is defined. Okay, that these two things, the Euclidean distance is also called the L2 distance. The Manhattan distance is also called the L1 distance. Both of these are actually special cases of something called the LP norm. The LP norm is you have 2 vectors, you take the difference of their absolute values, power p, add up all those things, and then take the pth root of that. If p equals 2, you get L2 norm. If p equals 1, you get L1 norm. If p equals 3, you get L3, and so on. You know, this is just a family of distance functions. And this is a distance, these are metrics in the formal sense, which means that they are greater than or equal to 0, and then they're symmetric and such things. Questions about distances between vectors. And if you change the definition of distance, you'll get a different nearest neighbors classifier. What is interesting is, then the question is, how do you know what to do? How do you, given a data set, how do you know which distance to use? And the answer is, typically you try not to think too hard about it. You just use L2 and hope it works, and unless you know better. Okay, that's about, one interesting exercise is what happens when p goes to infinity. When p goes to infinity, this function, L infinity norm, is also called the max norm. And an exercise to you is to simplify this LP norm expression when p goes to infinity. Questions? Have people seen LP norms before? Max norms? Yes? Okay.
What does it mean though?
What is what?
The infinity norm.
What does the L2 norm mean?
Euclid.
No, but what does it mean? It's the distance between 2 points. Okay, well, it's a straight line distance, but that's because we are conditioned into thinking that's the right answer. If we live in a universe where Manhattan distance was the way in which we measure distance, that would be the right way of doing things. One way of thinking about these things is, let's draw regions of points that are all marked at the same distance. In fact, let's pretend that one of those points is the origin. So I want to measure points. So let's say I have point x and I want to measure x minus 0 p naught, which is just the same as the p naught of x, right? And instead of measuring the distance, I'm going to draw points that are equidistant from the origin. If p equals 2, the Euclidean distance, you get these level curves that are circles. So all points on the circle are equidistant from the origin, right? So this is called the 2 norm ball in 2 dimensions. In 3 dimensions, the 2 norm ball is a sphere. What is the 1 norm ball in? So this is for the norm of x 2 equals some constant. That's the curve. I saw your hand and then you, yes.
So in 2 dimensions, it would be like a rhombus?
In 2 dimensions, it will be a rhombus. Yes, but
Oh, okay.
you said was it the same thing?
Yeah, so we have squares, then we have a, never mind.
But yes, in some sense, you are right. Your intuition is correct. Let's think about what is this thing equals a constant.
That'd be an octahedron, right?
It's actually going to be this picture, this thing here. And so on.
And as we go to infinity, we get to the square that
As
is.
we go to infinity, exactly. L infinity, so let's first think about 1. When L1 equals a constant, let's see why this looks like this. In fact, let's just pretend that the constant is actually 1. Okay? When L2 is 1, you get the circle with x1 square plus the x is the vector x1, x2. 2 square equals 1. That should be clear. Right? Now let's consider this thing. This is the norm of the one norm of x equals 1, which means the absolute value of x1 plus the absolute value of x2 equals 1. This corresponds to 4 lines because absolute value of x can be x or negative x. So really you have 2 options here and 2 options here. If you try all of them out, you get 4 lines. And when it's all equal to 1 is that diamond shaped figure right there. If you do L infinity, in fact, so this is L2, this is L1. What the intuition is, when P increases, this figure kind of widens out. When you go to L3, it will be a more, it will be a bigger something. I can't draw it. I don't know how to draw it, but it will be a figure that's actually outside the circle. As you go to infinity, it will be the square.
Isn't that called Chebyshev distance or something?
Possibly, I can never remember the functional form. So this is the picture for infinity equals 1. What does that mean? What that means is, so let's think about what is L infinity. Let me answer the question that any questions about this before I change the slide and get rid of the picture? So, going once, going twice, going thrice, gone. The L infinity is simply called the max norm. You take all these absolute differences between elements of the vector. You take the differences, take the absolute value, and the L infinity norm is simply the maximum absolute value difference. So it's the coordinate that is most where the 2 vectors are most different from each other. It's actually the difference for that coordinate. That's what this becomes equal to when the value of P goes to infinity. It's just another way of defining distance, and in practice, I've hardly ever used anything other than L1, L2, very rarely L infinity, and pretty much nothing else. Alright, so in the interest of time, let's also think about distances between symbolic features. How do you measure distance between categorical features? So, if you have bit vectors, if your features are all binary, you can pretend that they are all just vectors and take the Euclidean distance, but the most natural way of measuring distance between categorical features is to use what is called Hamming distance, which is simply the number of features that have different values. So let's say you have 2 vectors here, x1 and x2, and they are both identical except for color and orientation. There are 2 features where they are different, so the Hamming distance between these 2, x1 and x2, is 2. Fairly intuitive, right? Questions? Okay, so let me just quickly summarize what we saw with nearest neighbors. Nearest neighbors is a classifier. It's an instance-based classifier where training is ridiculously fast. You just add, take your training data and put it in a database. You can make this more complex and in practice you have to make this more complex by using some fancy indexing methods so that retrieval is fast. Prediction requires you to, iterate over the entire training set, find the nearest neighbors and make a prediction. what is interesting about the nearest neighbors classifier is that it can learn rather complex features. It can, rather complex functions like this function here. It's not linearly separable. It's a pretty nasty looking function, and the nearest neighbors classifier with basically doing nothing gets you that function. And the other advantage of the nearest neighbors classifier is that you always have the training set. Notice that in all other situations that we saw before, after you train a classifier, you throw away the training data, and you now use the model as the true function, and you make predictions. In nearest neighbors, you have the training set lying around, and if tomorrow you feel like you want to do something else, you can do something else with it. The problem with the nearest neighbors classifier is that it's actually extremely inefficient. It can be inefficient with respect to storage. I am not entirely convinced this is a real problem because storage, from what I hear, has become free. The real problem with the nearest neighbors classifier is that prediction can be slow. If you have d-dimensional vectors in your training set and you have n points and you are computing distances, for every example, you have to iterate over every training example, so that is n examples. You have to compute distances between the test example and each training example. That's roughly an order of the dimensionality. So the complexity could be O of d times n. And if you have more and more data, prediction becomes slower, which is a bit of a problem. In most other classifiers that we saw had the opposite situation. Training was slow, but prediction was very fast. Here it's different. And one important and kind of subtle thing is the nearest neighbors classifier tends to be fooled by irrelevant features, and we'll get to that in a bit. So, any questions about any of this stuff? If not, I'm going to skip this summary because, the one thing that I do want to mention is this is probably the first machine learning algorithm that was invented. Partly because it doesn't really take too much effort to invent it. It comes with an interesting guarantee though. If there are enough training examples, meaning as the number of training examples goes to infinity, the error of the nearest neighbors classifier will converge to the error of the optimal, that is the Bayes optimal classifier. You can't do better than the nearest neighbors classifier if you have infinite data. Of course, if you have infinite data, you have other problems because you have to iterate over the infinite examples to make a prediction. That's a different problem. But in theory, you can't get better than this. In practice, you have to use an odd k for when you're doing k nearest neighbors. Why? To break ties. How do you choose k? You use cross validation. It turns out in nearest neighbors, the actual features and how you normalize them can be very, very important because you might have features with different scales. If you have one feature that is the weight and the other feature that's height of people, and let's say the weights are in grams and the heights are in miles, these two, the weight will dominate the distance. So there are many, many variants of this. I think already in the class you guys invented at least 3 different variants, and you can there are many more out there. So let me talk about the decision boundaries of nearest neighbors, because this is a concept that you probably will see more if you take a class on robotics and stuff, but it's good to mention it in this context. Effectively, we are asking what's the hypothesis space of a nearest neighbors classifier. The thing to keep in mind is that the nearest neighbors classifier never explicitly builds a hypothesis. It doesn't build a function. It just stores the data. You don't store a function. But implicitly, there is a function that's being computed. And we can ask, what is the decision boundary of that implicit function? And the answer is actually, it computes the Voronoi diagram. And let's define this, let's see what a Voronoi diagram is. Let's say you have a finite set of points in some space. For a point, let's call this point here, the Voronoi cell of that point is a set of all points in the space that is closer to that point than anything else, than all the others. So, this point here, the red dot that I have this point here, is in the Voronoi cell of the point that I'm just calling A. This point here is in the Voronoi cell of the point B, and so on. The Voronoi diagram is simply the set of all possible Voronoi cells. So it will look something like this. It covers the entire space. Questions? The nearest neighbors classifier effectively builds the Voronoi cell, because if, let's say, this point is red, which it is, this is red, then all points in the Voronoi cell of that point will be closer to it than anything else. Which means the entire Voronoi cell is going to get colored red. And so on. So, effectively, what the nearest neighbors classifier, one nearest neighbors classifier does is it builds the Voronoi diagram for the space and colors each cell with the point that created the Voronoi with that particular Voronoi cell. And the boundaries of these Voronoi cells gives you the decision boundary of the nearest neighbors classifier. You first, then you, and then I think there was another hand. Yes. Yeah.
I think for the cell, is there any possible that they overflow with each overlap?
The regions where they actually overlap are these boundaries. So the boundary, this point here, a point on the boundary, is equidistant. Well, I don't think it is in this picture, but in theory it should be.
So what's the classification here?
Oh, because you toss a coin. Doesn't matter.
So I was wondering if the data was continuous.
If the data was, you mean if it was, what's the data?
The points.
Features or the features are continuous, yes. In this case, it's two-dimensional plane.
I got confused with because something I studied regarding segmentation. We take k-means, and what is that?
Okay, then we'll take that offline, because I don't want to bring up k-means. That's a bit of a sore spot because I couldn't cover it in class. But anyway, we'll take this conversation after that. The thing is, I think you're confusing k-nearest neighbors with k-means. And that's a very common thing. They're very different things. They're very different algorithms that just happen to start with k. Someone else had a question somewhere here? Okay. So, if you have k nearest neighbors, oh, by the way, this picture supposedly uses Euclidean distance, but as I just demonstrated, even that's not entirely correct if you consider these two things to be equal. But if you change the distance metric, the Voronoi diagram will be different. With k nearest neighbors, the partition becomes more messy. It also ends up partitioning the space this way, but it's a much more complex decision boundary. And to answer the question that you asked about points on the boundary, you just toss a coin. So, question for you guys. So I have 2 points. What's the decision boundary of the one nearest neighbor? It's just a line. Every point on this line is equidistant from the 2 points. So simply the line bisecting the 2 points gives you the Voronoi diagram. Alright, in the 10 minutes that are left, I'm going to try to confuse you. I'm going to talk about this idea called the curse of dimensionality. So let's think about why your classifier will make mistakes. One of them could be overfitting, and we have seen this quite a bit. Another reason why your classifier might make mistakes is something called the curse of dimensionality. And the curse of dimensionality is not like a single thing, it's just this collection of phenomena which have the following property. Ideas that seem to make sense in low dimensions, in 2 or 3 dimensions, can, not always, but can fail when you move to high dimensions. What might be intuitively correct in 2-dimensional spaces might not make any mathematical sense when you go to high dimensional spaces. And we've been talking about high dimensional spaces a lot. If you want to get this kind of an intuitive grasp of what high dimensional spaces are, I recommend this cute little book called Flatland. It's actually from 1884. It's a Flatland. It's called A Romance of Multiple Dimensions. It's a interesting introduction to the idea of the fourth dimension. In any case, so why will high dimensions be problematic? Of course, if you have high dimensional spaces and most of the features are irrelevant, of course that's a problem. If you have 1,000 features and only 10 of them are relevant, especially with things like nearest neighbors classifiers, the distances will be dominated by the irrelevant features, irrelevant distances. And so that's definitely a problem. But I'm going to argue that even if you have only relevant features, high dimensional spaces can be a little odd. Let me explain this with some examples. So, say I want to calculate, I have a box, a square in 2 dimensions, and this square contains a circle inside it. And I want to calculate what fraction of the points in this cube, or actually a square, lie outside the circle. In 2 dimensions, a cube is just a square and a sphere is just a circle. And this is an easy answer. It's simply the area of the whole thing. The area of the circle divided by the area of the square gives you the fraction of points inside the circle. And 1 minus that gives you the area, the fraction of points outside, and that's 1 minus pi by 4. Should not be rocket science. We can move this to 3 dimensions. In 3 dimensions, you have a cube and there's a sphere that's embedded inside the cube. And I can ask the same question. What fraction of the cube lies outside the sphere? I do the same thing. I calculate the volume of the cube, the volume of the sphere. This is, just to remind you, the volume of the sphere divided by the volume of the cube, and 1 minus the ratio gives you the fraction of the points that lie outside the sphere. For 2 dimensions, we had 1 divided by pi by 4. For 3 dimensions, it's become 1 divided by pi by 6, which is closer to 1, right? In high dimensions, distances behave in weird ways. I'm not going to prove it, but you should try to think about how to prove this. As dimensionality increases, the fraction becomes close to 1. At infinity, this fraction approaches 1. I mean, as the dimensionality approaches infinity, this fraction approaches 1. Now let's think about what this means. You have a cube in d dimensions, you have a sphere occupying the cube entirely in d dimensions, and yet most of the cube lies outside the sphere. Now, does that seem like an odd situation? What this really means is most of the volume of the cube in high dimensions lies far away from the center. The center of a cube is in some sense very sparse. There isn't any space in the center of the cube. Most of the volume of the cube lies outside. That's an unintuitive idea. Are there questions before I go to the second example? Alright, if this did not confuse you, yes?
What if you use a different distance?
Oh yeah, then you redefine the volume, but the curse of dimensionality still holds.
Okay.
Yes. Now let me give you a second example that talks about a similar sort of thing. This time, I want to ask what fraction of a unit sphere lies very close to the surface. In other words, what fraction of the volume of a unit sphere lies within radius 1 minus epsilon to the radius 1. So basically, this is a circle of radius f1, this is a circle of radius 1 minus epsilon, so you have this ring of radius epsilon. And I want to ask, how many points live in that ring? For a very small epsilon. Effectively, in 2 dimensions, that's simply asking what's the area of the blue region here, of this ring. And you know how to do that. It's simply the area of the full circle, which is pi, minus the area of the smaller circle divided by the area of the full circle. And what you get is 1 minus epsilon squared. Right? Okay? Now let's move to 3 dimensions. You move to 3 dimensions, in 3 dimensions what you have is you have a sphere and you have of radius 1 and you have another sphere of radius 1 minus epsilon inside the big one, and you're asking how many points or what fraction of the points lie between those two spheres in that shell, on the boundary. And I can keep going making this, increasing the dimensionality. It's not terribly hard to prove that as dimensions in d dimensions, the number of points or the fraction of points that live on the surface is 1 minus epsilon power d, where d is the dimensionality. Now let's think about what happens when d goes to infinity, or as d becomes larger. As d becomes larger, 1 minus. So first of all, 1 minus epsilon is a number between 0 and 1. You keep multiplying it with itself again and again. The more times you multiply it, the smaller it gets. As d goes to infinity, that number becomes close to 0. Which means, as the dimensionality goes to infinity, the fraction of points that lie on the surface of the sphere is 100%. As the dimensionality increases, you take a sphere, and inside of the sphere, just mathematically, is hollow. All the majority of the points lie on the surface of the sphere in high dimensions. And this is also weird. Basically what this means is most of the volume of the sphere is far away from the center. If that does not make you uneasy, you are much stronger than me. So let me just wind up and talk about the curse of dimensionality. What mathematical perspective, most of the points in high dimensional spaces lie far away from the origin. In 2-dimensional spaces, on the other hand, most of the points actually lie close to the origin, because you could see that picture. Most of the circle was close to the origin, was the white region. Which means that you need more and more data to fill up the space, which is actually very bad news for nearest neighbors classification in high dimensions, because the idea of a neighborhood is kind of messed up. If most points lie far away from the origin, most points are equidistant from each other, because they are all lying on the surface. The neighborhood, the closest point could be a point that's actually very far away. And that's problematic, because you're saying that the label of the closest point should be the predicted label. And there are also computational problems as the dimensionality increases, and unfortunately I'm not going to get into that. One way of dealing with the curse of dimensionality is to recognize that in real life, points don't really lie on, even though points might be in high dimensional spaces, they might be embedded in a lower dimensional space, and so you can, this line is from an earlier incarnation of the semester of the class. So one way of handling this kind of a problem is dealing with using ideas like dimensionality reduction. Another important thing that you should use is feature selection. It's an art, it's a black art. You need to figure out what are good features, and adding noisy features is going to be problematic. Possibly, prior knowledge can help. If you have prior knowledge about the hypothesis, then maybe you can guide your classifier to not even using those irrelevant features. Any questions about this? If not, I can wind up and just summarize nearest neighbors. It's the oldest algorithm out there. It requires a distance metric. It partitions the space into a Voronoi diagram, but be aware of the curse of dimensionality. This was a very tiny lecture on nearest neighbors, but it's a somewhat easy concept if you don't think too hard about it. You can make it rather complicated if you start thinking about the curse of dimensionality. But at the basic level, the nearest neighbors classifier is so simple, you can probably implement it in the next 20 minutes. In fact, if you want, you should try doing that for your project. Alright, I'm going to stop. I have office hours now, so you can come to my office. And there's a homework that's due today, so maybe you don't want to implement the nearest neighbors today.